I just want to share something. I had a question from a student, and then yeah, so cool. Yeah. So first of all, I am Matthew Skull. I am a lecturer at CPUT, and yeah, I am obviously doing this on a part-time basis. Um, I've been teaching for 5 years. I've taught plenty full subjects. I think one or two of you guys might know me. Yeah, I've taught the subject as well. Obviously in a different capacity in terms of the content, but essentially the same. And yes, that's essentially it. I just want to confirm something to you. Can you guys see can you guys see anything here? I'm sharing this thing from the book, an ebook. Can you guys see that? Yes, okay. Roderick, Gerald, Zinke, Ronwan, Lyle, I don't know, Mohammed, Wanya. Can you guys see it as well? I believe I'm also audible. Cool. So N6, right, obviously is in fact, it is a continuation of N5. And these are the modules you're going to have to know, right? So module one, which we are starting on today, um, which is thick cylinders, continuation of something called thin cylinders. We have tension in cables, which is a completely new section on its own. Yep. Uh, and where am I now? Yeah. And you can see that's quite small. The third module is combined bending and twisting of shafts. Possibly my favorite. We have bending and deflection of beams. Again, over here, make sure you revise your bending stresses in N5. Likewise with module 5, which is combined direct and bending stress. We also have shear stress in beams, right? That's a new section. We also have closed core helical springs, another new section. We have transformation of stress. And if you covered module 4 in N5, I think you were introduced to the Mohr circle. In this case here, you're actually doing the formulas for Mohr circle. And then module 9 is the forces in structural frameworks, which is a continuation, I believe, of module 8. I do want to make you aware that I'm not going to cover this module, and I don't cover the module as well on the N5 side, because this requires you to have, in fact, if you want to teach yourself, which you're supposed to be, some set squares, protractor, and basically that, yeah, particularly for module 9. And for module 8, will require you to do uh, a Mohr stress circle. So this is the essential syllabus for N6. It's a lot. There are a lot of subsections, and it's going to require a lot out of you. I can assure you that. Another thing that I'm thinking now is when I look at the questions asked in the past papers, the best thing you can do is make sure you tackle what you know to get 50%. In fact, aim for 70% to land on 50. I mean, getting a distinction is not going to make a lot of people's lives better. So when you're preparing, I believe that's the best approach. I've seen, yeah. Okay, that's the syllabus. I'm not sure if you guys are familiar. And then before we start, I do want to make you aware what's supposed to happen is that you guys are supposed to prepare on your own, and then give me questions and I can solve them for you. However, I did do this last trimester where I kind of send you questions and we kind of go through it. So just remember what I'm doing here is essentially 25 to 30% of what is required of you to pass, right? You need to put in the other 70%. Look here, it's a lot of stuff. I do want to share something briefly with you as well, something I just quickly developed. as a means for you to monitor your progress for the subject. Because remember the trimester short. And I normally teach this kind of stuff in 6 months, 12, 14 weeks. I don't know how you guys are going to do it in a short time, but I mean, you guys are used to this game, so make sure you, yeah, put in the work. So what I have done here, and if you're interested, you can obviously, you can just message me in the WhatsApp group and I can talk about it. So it's basically a past paper tracker, and in essence, what you do with this is I have 2019 over here, and I have obviously the trimesters of where the exams are written. And you decide you want to do 2 or 3 questions a day, right? So for instance, let me just remove these, just make this white. And you're going to decide, let me just do this further. Yeah. So you're going to have to decide, okay, today I'm going to do, let's say obviously we're doing 6 cylinders. And so therefore, your aim is to do 2019, 2020, 2021. That's 3 questions after our session, right? In fact, till 2022, 4 questions. You attempt the first question, you see how it goes for April 2019, and if you can solve it, you gooi a green, right? If you get most of it, but not all of it, you gooi a yellow. If you get 50% to 60, you get you put that there. So let's say you do that one. And then the idea is that as you populate this, right, it's going to inculcate discipline in you, because if you clap the past papers, you surely would be fine. You know what I mean? For the rest of the stuff. So just something I thought about, maybe it'd be useful to you, because I mean, if you do practice most of the past papers, you kind of get the gist of what's required of you in the exam. But this is above and beyond your practice in your book. I will post something on my other recommendations regarding this. Okay, so is there any questions before we actually start solving problems? You can unmute your mic and then, yeah. Let's just check Zinche, Charlene, Franco, Gerald, Ayapukwa. Any questions before we begin? Anything at all?
Nothing yet, sir.
Sure. Okay, I don't know who that was.
Ayapukwa.
Oh, okay, Ayapukwa. Okay, great. Lyle, Pubele, Ronwin. Okay, well, seems like not much. Okay. So what I'll do for this session, I will go with standard lecture style and I will talk you into the topic. But like I said, right, you are unfortunately expected to do this work yourself. I do believe in my teaching style where I kind of just introduce the fundamentals just to kind of recap what's happening here. And then we're going to go into solving problems. That is the majority of our sessions. Your notepad, your calculator, your pen will be, yeah. You're not going to sit and listen to me. That's no way. You're just wasting time. And as you solve problems, you have questions. And I would like for you guys only to contact me between around 5 and 7 or 8, maybe the day before our session, so I can answer any questions. I mean, I have other commitments as well. But I'm not essentially always available, but I'm available when I'm there. But the main thing is you must put in the work, see what you know, see what you don't know, and then we can tackle those particular problems as a collective, right? I would like everyone to pass the subject. A lot of people feel, well, got at least 3, 4 guys over last trimester on N5, but you have to put in the work. That's given. Yeah. Okay, so let me just do the small lecture and then we can actually just begin. Okay, so I got this on something called SlideShare. And yeah, So we're looking at pressure vessels over here. It's quite fortunate for you. I've worked in this industry where we build vessels, but I worked in a capacity of testing the materials and welding mostly, right? But I can still remember most of the things which is done. I'm sure we're all aware of a common pressure vessel, a boiler, which used to produce steam under given pressure. And I think we've all seen a boiler. That's essential pressure vessel. There's a lot of other types of pressure vessel. One of the main design codes, or in fact, like the gold standard for designing pressure vessels is particularly it's a code they use ASME 8 Division 1, and that articulates everything when it comes to design of pressure vessels. In fact, they have a definition of pressure vessels, and it's over there, and it states that pressure vessels are containers for the containment of pressure, or external or internal. Very important. The pressure may be obtained from an external source or by the application of heat or from a direct or indirect source, or any combination thereof. And it's amazing that they actually show that there was some explosion happening in a pressure vessel. Pressure vessels are, when I worked, it's a very, very quality assured design. There's quality assurance at each individual process. So yeah, it's something, it's a big deal. It's another mechanical structure, but again, it's designed with a lot of care. Okay, so pressure vessel. So in the last series of strengths at N5, we look at thin hull pressure vessels. If your tutor or you taught yourself, you knew that well. Basically, when your diameter thickness ratio is equal to or greater than 15, it's known as a thin cylinder, right? However, if it's less than that ratio, it's known as a thick cylinder. I must make you aware that the ratio is typically considered from 10 to 20, it's still arguably subjective. However, that's the difference between a thick and a thin cylinder. By a thick cylinder, you'll see the thickness of the plate used is a lot thicker, right? So obviously you're exposed to thin hull cylinders, and they are both analyzed analytically with two different types of procedures. I don't want to go into materials, but then again, you guys can have a look at this, right? These are just stuff, you know what I'm saying to you, things you have to know. Very good set of slides. This is exactly how pressure vessel looks like. I've seen this on SolidWorks drawn exactly like this. It's drawn on a modeling software, and we do all the tests and stuff. Okay, now in a thin, the purpose of strengths, obviously, I don't know if you guys know, there are 5 fundamental loads in strengths or in mechanical loads. One is a tensile load, one is a compressive load, one is a shear load, one is a torque load, and one is a bending load. We do have other 2 loads. They are secondary loads. One is a temperature load and one is an internal pressure load, pressure due to a liquid or a gas. This is what we're looking at, right? So in essence, there are 7, but 5 fundamental ones. Okay, so you have a vessel or a pipe, you load it up with some fluid, some gas, and what's going to happen, right? You obviously can imagine that the pressure of the fluid or gas will exert some force on the walls, and then obviously it will induce some kind of stress, right? And 2 stresses happen in thin hull cylinders, right? Before we get to the thick hull. The first one is a circumferential one, and the other one is a longitudinal one. Okay, I think we're familiar with that. So I'm just going to quickly go there. So this one is a circumferential or hoop stress. I think you guys are familiar with. And what it does, it wants to split the vessel along circumference. So it splits it like that. That's the purpose of what's happening. So it splits it that way. I don't know if you guys can see. Your longitudinal stress wants to, well, this is still the hoop stress, right? So it splits it that way. It splits it, I don't know, in 2 halves that way, right? I don't know how to mention that, right? So the stress acts that way. Then on the longitudinal side, Again, this is the formula for it. I believe you're familiar with it. It looks like this. You've seen this before, right? On the longitudinal side, it wants to split it that way, right? So one that way, one that way. Okay. And it's yeah, and these are the formulas for it. I mean, essentially for both, it's pressure times diameter divided by 2 or 4T. Why is this important? If you ever look at anything like a pipe under pressure, right, and it fails, it typically fails here. Here's Mohammed. Wayne.
So for the longitudinal pressure,
Yes.
if you have an internal and an external pressure, which pressure would you use in the formula?
So we're gonna get to that. So we're just discussing the basics here, right? We'll get to that part. We're just going over the N5 stuff, right? We'll get there. Okay, cool. So then this is analyzing Thunhold. I'm just giving you again. I'm in a lecture fashion, just reminding you of certain stuff, right? And then we're gonna get into the meat and potatoes now. Okay. You just go back. Where am I now? So then going to Thickle, right? So these are some examples. Here we go. So in a Thickle cylinder, right? Here are some examples of Thickle cylinders. There's hydraulic cylinder, gun barrel, a pipe on both sides when it's subjected to very high internal fluid pressure, right? And if that is the case, the holes of the cylinder must be made extremely thick. So when you're dealing at the pressure, we want to increase the hole thickness. Now, in the previous one, right, we only had two types of stresses, the hoop stress and longitudinal. However, here, when you're dealing with a thick cylinder, you're having a stress through the thickness, which is called the radial stress, right? That's what this is about. So thick cylinders have radial stresses, and in thin cylinders, we essentially say that the radial stresses are insignificant. Very, very important. The analysis we use, there are four types. That's Lamai's equation, Bernoulli's equation, Claveriano's equation, and Barlow's equation. I believe we stick with Lame's theory. And what is Lame's theory about? It's basically used to find the stress across the thickness of the vessel. Why is this important? Is because it's most likely to actually break through the thickness, in this case, in a thick cylinder case, right? And what's important here, they say, is that it's a maximum at the inner surface, and well, this is for the hoop stress, sorry, and it has a minimum for at the outer surface. Then looking at the radial side, which is typically compressive in nature, which is very important, you'll see that it's a maximum on the inner surface and zero on the outer surface. That is the stress distribution. The reason why this is important, so when you do your calculations, you're able to see, right? So again, this is for the hoop stress, and this is for the radial stress. Okay, there are assumptions made in the analysis, which I'm not going to go over, and we will look into that. So that's the basic stuff. I'm gonna talk to this one, and then we're gonna start solving problems immediately. So this is going to Mohammed's question there, and those are the two formulas you're going to use, right? So one is going to be for your hoop stress, which is A plus B over R squared, and then your radial stresses as A minus B over R squared. Okay, and we are typically have to find these A and B's. Again, what's not shown here, right? That A is actually your longitudinal stress. There's a formula for that. But with more experience, you'll see. What we're also going to look at is both internal and external pressures acting on a thick cylinder. The reason why this happens is because when you do thick cylinders, it can kind of what's the word I'm looking for? It's designed for that purpose. A thin cylinder won't work in an external pressure case. It'll probably break. Okay, so this is the meat and potatoes. There is a bit more stuff, but we will talk. We will, as we solve, we will learn. And what I expect is for you to engage. If you don't understand, you can stop me and we can talk through it, right? I'm hoping to solve at least 4 of these examples, and then we're done. So again, before we commence, right? I'm doing this in lecture fashion. Typically, you can send me questions, then we solve them. Given that you went over the theory, but I'm just being kind to go over the theory so that you have an understanding of what's happening here. And you can let me know what is your preferred approach. Should I go over some basics and then we can solve, or you guys would do the basics and we can solve all the high-end problems, right? And obviously I want to have enough time to solve everything. I will say now, and I like everyone to take this very seriously. Your up and coming test is going to be thick cylinders of the compound fashion, right? So we might not get it today, but make sure, absolutely sure, you can do compound cylinders for thick cylinders, right? Is that clear to everyone? Can't see anyone here. Okay, cool. Be very clear. Compound cylinder is going to come in. I will give you some more guidance later on, but make sure once we do this, get to the compound side immediately without fail, right? The reason why I want to start with this, the fundamentals are always important for you to understand the harder stuff, right? All right, can everyone see my blackboard or whiteboard? Just confirm. Can someone just say yes, because I can't see your thumbs up.
Yes, sir.
100%. Okay, let's begin.
Yes.
Okay, so I'm working from the P. de Toit book. Charlene, is this probably some of your families who developed this textbook?
No, sir, it's not.
Okay, I'm just checking. Right, so let's begin. Right, so we're doing thick cylinder. Let's use example 1.2 in the Toy textbook. Right, you can use a Vickens textbook; it's equally as good. But I just chose this one. This is what I got from the institution. So let's quickly begin. Right, so the first thing we do, we call a cylinder. Right, we draw one. Just bear with me. My cylinder might not look like a cylinder. But yeah, okay, there we go. And I'm deliberately doing it, I'm making it thick so we can see it's a thick whole cylinder, right? So what we have over here is an internal diameter of 250. We have an external diameter of 350. Okay. So before we begin, I always find it disturbing that students cannot do this. I see Mr. G has joined us. Mr. G, are you here for a lecture on insects?
No, I was just passing by. Say I'm leaving now.
No, you can stay and listen, man. I will teach you something. And so, okay, right. So in this case, in this particular problem, we have an internal pressure. I'm just going to throw this in for you, right? Just like this, right? Again, we're going to be dealing with internal and external pressures. So with that being said, like I said to you, we're going to get two stresses in this guy. One is radial and one is a hoop stress. Okay. So the first thing is, we start with typically the radial, and the base formula starts like this: A minus B over some diameter squared, right? That's going to be your radial. I'm just going to put a big D. Then we have our hoop, which is going to be A plus B over some D squared, right? Mohammed, is this the question you are asking? I don't know, external. Someone asked me in the group about formulas. Yeah.
I was asking about question example 1.4.
Okay.
Yeah.
Yeah, we'll get to that one. But
We'll
someone
get there.
asked me about the confusion of the formulas in the group, man. This is what I'm
It
actually
was me.
thinking of.
It was
Who's
me,
that?
Warren.
Warren, are you happy now with that?
Warren. It was me.
Is this the question you're asking?
Because this is the question asking. Because in the other textbook, because I got both, the one has the minus, and the other one has the plus. The hoop and the radial is totally different.
Okay. Let's solve and investigate further now. You know, books can be wrong, eh?
Yes,
You're never wrong.
That's right. Cool.
Okay, so how do we start this analysis? Guys, this analysis begins the same all the time. Now, I want to just put something here for you, man. Right? Just give me a second. I want this to be in your mind all the time when you're solving these problems, so that you always know that when you're right and when you're wrong. I just want to get a picture here, go. Why am I not seeing this thing now? Okay, just give me a second. It's loading. Drawing the stress distribution will give you some kind of solace, some kind of peace, so that you know what's happening here. Just give me a second. The Vickens book does it nicely. Just want to get to it. Just give me a second, okay. Right. I'm just going to paste it. Again, this is all ebooks. I don't have a soft copy. There is no soft copy. Okay, so this is the stress distribution. And this is for internal pressure, right? We need to talk about external now. So again, looking at the stress distribution through a thick wall cylinder, the radial stress is a maximum at the inner diameter and it becomes 0 at the outer diameter. The hoop stress is a maximum at the outside and then becomes a minimum. I think this is correct. I'm trusting. Oh, sorry, it's the other way around. So from big D to small d, you can see over here. Yeah, from big D it's a minimum to small d it's a maximum. That's what I meant. Big D it's a maximum for the radial and it's a maximum radial stress at the small d. Very important. Know this, right? This is for the internal pressure. We're going to talk about external pressure, hopefully. In fact, we're going to get there. Okay, are we happy with this? So know this. How do we tackle these problems? They all typically start the same way. Let's start with the radial stress. Radial stress, again, I did mention the radial stress is compressive in nature. There's a reason why. We can maybe talk about it again. So it's 15 times 10 to the power 6 at 250. Again, I know it's the maximum because this is the smaller diameter, right? At the bigger diameter, which is 350, it's 0 megapascals. I should have put here pascals here, but you get the idea. This is at 350 millimeters. Again, you should be writing with me as we go along, okay? And then let's begin. So the first objective of these problems always, and I'm saying always, you have to find your A and B constants. Get very familiar with this. So what do? We first set up we're going to use this equation. Remember, radial stress has a negative in. There's a reason why, right? So let's quickly start. So if I say 15 times 10 to the power 6 equals, right? That's the radial stress. It's equal to internal pressure. I should have said that. It's A minus B over 0.25 squared. This will be our first equation. My next equation is at that'll be 0 equals A minus B at 0.35 squared. That's my second equation. We then have to solve this two simultaneously. Students, are you following so far?
Yes, sir.
100%. Okay. So what I want you guys to do for me now is solve A and B. I'm not going to do that. You guys can do that. And if you don't know how to do it, you should be able to know how to do it. Anyway, what you must do is Gooi this one to the other side. You're going to have A over here at equation 2, substitute that into equation 1, and then solve for A and B. Okay, let me know when you're done.
You want the values? Do you want the values, sir?
Yes.
Well, I got B was 1,91 times 10 to the power 6.
1,9 times 10 to the power 6, right? And
Yeah,
8.
and A was negative 15.625 times 10 to the power 6.
It shows negative 15. Can we collaborate that? Yeah. Can other students, you said 15 point?
625.
625.
Times.
Okay.
Yeah, times 10 to the power 6.
Can you guys just check that? We can't trust everyone here. B must be positive. I'm looking at if B is positive.
You can trust me, sir.
A can't be negative, man. Something doesn't look right there.
A is 8.163.
Definitely not. You're wrong. These answers
Oh,
are
you
right.
want you want the full value. Oh, it's 15.625 times 10 to the power 6.
100%. Is it positive or negative? That's what I'm asking. It's positive.
Positive.
It should be positive.
Yeah.
The reason why, I'm not sure what that was, is because if you say A equals B over 0.35 squared, right? If you substitute this in, it's still going to give you a positive value. Are you with me?
Yeah, because if you take A over, it's a negative, and a negative turns it to a positive.
Exactly.
Yeah.
Right. I'm not sure. No, you're right. I don't know what that is. Yeah,
so I see what that the other student was saying, because for my radial stress formula, I have pluses.
Oh, I
from
see.
The textbook.
So now remember.
Yeah,
right?
so that's why mine is negative. Because when I did equation 2, I had A equals negative B over 0.35.
I see. So can we see already, right? Negative and positive for the radio. Are we happy with this? I believe
Yes.
this is correct. Yeah. Yeah. Anyway.
So the radial is negative always.
Yes. There's a reason why. I'll try to show you. If I can. Are we all happy with this?
This book of Mr.
Wickens.
Henry Wickens.
Yeah. You see sometimes
His formulas are different.
If you go to
different.
page 4, it's exactly the opposite of what Mr. Scholes is saying.
Okay. Interesting. Let me go have a
if you
look.
go to page 4, Lame's equations, it's other way around. It says radial stress is
I see. I'm looking at it.
A plus B divided by D square, and that's
Yeah,
why
that's where I got it
wondering.
I see.
That was confusing me as well, sir.
I see. Okay, right. It's fine. I do see it. But let's proceed. Let's see. I see it, yeah. Okay, cool. It's fine. So let's see what answers we get. Anyway, so once we have that, I forgot what the question asks again. I keep on forgetting. It says calculate the maximum stress in the cylinder or and sketch the stress distribution. So obviously we have the radial stresses, right? Which is that too. Now I have to calculate the hoop stress. Yeah. The hoop stress. And that's gonna be as I said, A plus, right? B plus over the diameters now, right? So one is gonna be at a minimum and one's gonna be a maximum. So again, looking at your sketch.
Big D.
Yeah, so let's start with big. At big D, it's a minimum, right? So we're gonna say at 350. It's a min. And then at what's the other one? What's the other guy again? 250. Thank you. 250. It's a max. My colleagues and students, can you see how important the sketch is? It tells you the story, right? So you know. You know what I mean? You'll see. All right, so you guys can just substitute now A and B in here from this. A goes in here. B goes in here. I think that's positive in our case. And then let's see what we get. So I'm just going to go here at, you guys going to do this for me. One is at 250, because this is at 350, sorry. And this one is at 250 mil. So just plug in and do it. I just want to start, I'm going to just check something, but I'm pretty sure that, yeah. Just want to go through, just confirm something. Let me know what the hoop stresses are. Pukwa. Yes.
Yes, sir. Sir, I just have a quick question.
Yes.
Since the hoop stress is maximum at the small diameter and minimum at the big diameter.
Yes.
So since they're asking for the maximum stress, do you have to work out both?
No, you don't. I'm just being like, you know what I mean? Like I'm just showing you all the possible options. Yeah. You don't have to work out both. Yeah.
Oh, okay.
Yeah, it's a good question. I'm just showing you like, you never know. These things can happen.
Okay.
Yeah. Does anyone have the answers? I'm gonna take a snapshot as well of this thing here.
I get my max 46.249.
Righto, okay.
249.
Yes.
And then for min I get 31.249.
Okay, cool.
So it's the rounding off that.
No, it's fine. Don't worry about that. I'm not concerned of rounding off. It's something I am concerned of though. So I'm waiting for the house to get there.
I have the same answer.
Fantastic. Okay.
For the maximum.
Cool. So can we see there, right? That she's just summarizing the whole story for you. Can you see? This is through the thickness, right? Can you see that there's a 46.25 maximum at there, and it becomes a minimum on the outside, right? That's what I think that's what you said, no? 31.26. So the maximum is 46.25. The radial starts at a maximum here and goes that way. Is this correct? But there's something I want to bring up. Let me just quickly see here. Maximum. Oh, they flip this around. I see. Big D should be the minimum. Yes. And then the maximum should be at the small d. Yes. Okay. Okay, that's fine. That's fine. Who's here? Okay. Are we happy?
Yep.
Yes, sir.
Okay. So yeah, what's important here, my students, is that once you have these stresses here, one is going to be at 350. What do we have again? 31.25 MPa.
Yes.
And this guy we had 26 whatever, 46.25 MPa. It's important to put the sense here, right? So the hoop stress is tensile, and sorry man, I made a mistake. It's supposed to be H, not R. Let me just erase that. Okay, that's H. Yeah. So the hoop stress is tensile for both maximum and minimum. The reason why is when we do the external stuff.
Is
Yes.
Is tensile given the positive notation?
That is correct.
The positive.
Or it's supposed to be like that.
so in the textbook it says compressive is given the positive notation and
I see. It doesn't make sense
tensile is
to
given
me.
a negative
It doesn't.
notation.
Yeah.
Yeah.
It doesn't make sense to me. Yeah.
For external pressure, it's the correct way around. For external pressure, it's the proper way. Tensile is positive and compressive is negative.
It's a mess actually. I don't know why I did that because tensile is always
It
deemed
was a bit
positive.
confusing.
Yeah. Compressive is always deemed negative. I mean, it's just like that. But I knew there's something with the sensors, man. Okay. Are we happy with this? Do we feel good here?
Yes.
Okay.
Yes, sir.
All right. So let me just see the questions now. And we're going to do the next one. All right. Is there any questions before I move on? Let me just quickly see here. I'm not so. I think we're gonna skip 1.3 has external. Okay, cool. Let me do that then. Okay, cool. Let's do 1.3. So, guys, the first question was.
1.4 also.
Yeah, I'm gonna do all three. Don't worry. 1.3 is external pressure now. So this particular one is when we had a cylinder and we subjected to an internal pressure, right? Is that clear to everyone? And now we're gonna do one where we're doing external on its own, and then the next question we're going to do where what's the other one? We're going to do it's both. I hope we both on the same page here. Okay, so what does this look like? Let me see what the Vikens book say. They might have a distribution. Let me quickly look. Yeah, it's good to use two textbooks. It seems like it's helping. Okay. So I think it's Muhammad I think that's him who asked that question. So guys, we did internal, we move into external pressure. Next question, we're doing both, right? Yeah, there's people joining like no one's business. Okay. So we're here. Let's see. Again, we have a thick cylinder. We've got an internal pressure. Can we see over here? Where is it over here? Right? And on the other side, we have external pressure. Can someone perhaps tell me why this would happen in a practical sense? Where do we see this? External, internal. Where can we see this?
In a
On
pressure
bushes.
vessel.
Let's here. Let's just check who's that first. Yeah, I'm waiting.
In a pressure vessel.
Yes, but which type, man?
A low pressure vessel.
Yeah, but like where, like what's the equipment called? Heat exchanger, or you know what I mean? A hydraulic cylinder, what? Okay, that's fine. Okay, anyway. So when you're looking at external a thick cylinder, this is what happens now. So our stress distribution is a bit different on the external side. What do we have now? Looking at this, they say here, with an external pressure, which is the maximum pressure, which is radial stress, will be on the outer diameter, right? And the radial stress will be 0 at the inner diameter. I believe that's what's going on over here. Is this correct? Is it showing the right? Oh no, this is over here. This is internal pressure. So we're external, sorry. So again, it's now minimum at the inner, 0 at the inner, and then maximum at the outer. Can you see the distributions are a bit different, right? And then when we look at, what is this thing called? On the other side, it'll be a minimum on the outside and a maximum on the inside for the hoop stress. Now, what is important is that now in external setting, the hoop stress is now compressive and not tensile. Is that clear to everyone? Are we happy with this?
Yes.
Thank you.
They're both compressive now.
Yes, that's the difference with external. Very important.
They're both compressive in external.
Yes.
Okay.
And you understand when we do both. So just remember. Yeah. Okay. And again, having a distribution.
So they're both negative.
Yes. Yeah. Okay. You'll see. It kind of works out, but you'll see what I mean. Let's just move on. Okay. So that's the point. That's the main point here. Okay. Let's just move on. So let's begin the example. So it says a thick cylinder is subjected to external pressure of 30 megapascal. The outside diameter is 400. Inside is 200. We have to calculate the hoop stress at the external, internal, and mean diameter. Okay, mean diameter is the average diameter, which we can work out from the same time. Guys, just a recap. Some people tend to forget this. Know that thickness is equal to big D minus small d over 2, right? Just remember this. Am I right? Over 2, yes. Sometimes they give you thickness in the questions, and you have to work out the small diameter. So I'm just making you aware of this. Some people forget this, which is kind of obvious if you think about it. So let's do the same analysis. Okay. So for external pressure, right? So we have our radial stress. It's still going to be A minus B over D squared. The conditions are as follows. At 30 megapascals radial, this will happen at 400, okay, which is the outer, right? Again, that distribution. You see, the maximum. At 200, it's going to be 0. I hope you're happy with this. And then based on that, we can quickly just find our A and B constants, right? That's the aim of the game. So we know that's minus 30. That's A, which is the longitudinal stress, which is not shown there. We have B, and then we know that's at 0.4 squared. Equation number 1. Equation number 2, 0 equals A minus B over 0.2 squared. Equation number 2. Can I have my A and B constants, please? Students, are all happy? Are we all okay? Is there anything on your mind which is burning?
B is
Okay.
minus 1.6 times 10 to the power 6.
So if someone is asking whether the stresses will be compressive or negative, our numbers will talk to us whether it's negative, positive or negative. So you don't have to worry about the sketch. The numbers will talk. Anyway, A
is 40 times 10 to the power 6.
Positive or negative?
Negative.
Yes, exactly. This is what I'm looking at. Okay. Mr. Toy, can you please confirm this? And Nathan. Moses as well. Moses is yes. Ronwin. You can't trust David, Mr. Warnikerk.
Why not? All my answers were right the first time.
Ah, man, it's too soon. Because we have to poll test. No, but for sure, man. I believe I'll be trusting you for the rest of the trimester. Gerald, Yes, he says yes. Okay. Let me commence, right? So then, Ms. Bono, are you with us? Let's find our hoop stresses. And we can just plug the values in, right? But we do know for external pressure, the maximum will be at the inner. Anyway, but let our numbers will talk to us. So we know this is A plus B over some diameter squared, right? So A minus 40 times 10 to the power 6 plus, we'll just keep it negative, 1.6. Can you already see it's going to give us a negative answer, right? We go in the, what diameter? It's the 0.2. We get an answer. And then we do the same here. I'm just going to say hoop again. This is at 200. Other one was at 400. 40 times 10 to the power 6 plus 1.6. Again, you could have made this negative and kept that a positive, but anyway. That, and that is 0.4, I believe, right? Okay, so can we get the two stresses there?
The hoop stress for minimum,
200.
it's minus 50 megapascal.
Is that for 200? What is the minimum?
That's the bottom one, that one.
Okay, yeah, yes, I'm
It's
listening.
minus 50 times 10 to the power 6, which is megapascals.
Okay, so it's 50 MPa. You said it's negative, right?
Negative, correct.
We know it's
which is a
compressive.
compressive. Yeah.
Exactly, beautiful. And then we go our hoop. I mean our at 200, which is the maximum, I think, or not. I think that's a minimum. So what is our maximum then? On this one?
Sorry. On your hoop.
Yes, the 200.
80.
80 what? Compressive, right?
Yeah, minus.
Okay, there
That's
we
right,
go.
compressive.
Okay. Let's just give 2 minutes for people to catch up. Ashinda, Roderick, are you guys here? You thought you came to play today now?
Yes, sir. Yes, sir.
Welcome. Welcome to N6 Chief.
Are you doing the mean also, sir?
We will do the mean again, man. Don't worry. It should be easy to do. I'll talk to it now. I just wanna let people breathe first here. Do the mean just now. Is everyone happy? I'm happy that people are actually studying. Oh, it's another one. Okay. I'll be content. Okay. I'm assuming everyone is happy, all right? So now let's look at the mean. So the mean, D mean, right? This is just the average diameter, which is going to be 400 plus 200 divided by 2. That will give us 300. Okay. And once we have that value, we simply just chuck this value into here, right? So the hoop stress at the mean will be A plus B, which you know already, divided by 0.3 squared. And I don't know what the mean hoop, so yeah, what's the stress at the mean?
Negative 57.78.
Negative 57.7. Okay, again compression. Right, I'll just okay. The sensors are very important. Yeah. Okay. So luckily with this approach, you can see it comes out compressive. colleagues, are you happy? Mohammed, Pubele, Moses is happy. Zinke?
Yes, sir. All right.
Good. Ayapukwa? Great. Okay. So the next problem, right? What I want to make you aware, the approaches are essentially the same. We're essentially going to combine this approach and that approach. And in the end, we're just going to be adding that stress and that stress at the same diameter, that stress and that stress at the same diameter. You'll see what I mean. What's important is you get the senses right. And it looks like we're going to be running out of time until 7. So we're going to be possibly ending off for this example. And then there's probably another small one, which I'll talk to some theory. And then, yeah, you guys must carry on. But you'll talk after that. Here for 1 hour. So let's do example 1.4. But are you guys feeling good so far? Am I bringing some light?
Yeah.
Okay, I'm happy.
Looks good.
I'm happy.
1.4 is not nice though.
Don't worry. The Lord is our Savior. He makes the way.
Right, yes, that's right.
Yeah, he makes the way. Okay. So now we have a cylinder, closed ends, hence pressure, and is subjected to an internal and an external pressure. This is the bad boy. Not even the bad boy. You must not get a compound cylinder. But anyway, you'll see. Can't wait to get to that. I do want to do a compound one next week, even though we're supposed to move on to the other one. But anyway, I'm gonna squeeze him in. How do we begin this? The analysis is the same, right? But now we're gonna have external part and an internal part. So we start with the internal, as you know, right? You can write internal pressure. I believe you know how to write internal. And the analysis is the same. We know at the internal, right? The radial stress on the internal side will be -8. Sorry, it's negative 160.
Yes,
yeah.
megapascals.
Megapascals. And that occurs at 150 at the internal, right? Can you see what I'm talking about? That distribution is important. Can you see that? For the internal, remember this? Small d? Yes.
Yeah. Excuse me, sir. Can we draw the sketch of that? Because I normally work out that when I see something, then it works.
Okay, cool.
I can't see that thing. Because they give you now an external of 80 megapascals after that.
Don't worry. That's why I'm here. You get me as a bit off center, but right, you should be happy.
It's fine.
Okay. So inside here, right, you've got an internal pressure. Okay. Some fluid is acting here. This is 160. Okay. Okay. On the outside, right, got something else happening here. Let's be submerged in something else, and that's providing another pressure. And that pressure is going to be MPa. That's going to be 80 MPa. Okay. So that's P out, P in. Okay. Now, when this happens, when you get stresses in the walls, this is what this is about, right? And of course, there will be a hoop stress acting. I'll show you what it looks in a 3-dimensional way. After let me show you now, so you can actually see. There's a nice sketch in the toy. Things we talks about strain, I believe. It's an element. Okay. Just so you can have a look at the feels a bit funny to me, but anyway, I'll just go with the sketch and verify this. But anyway, so in the wall, right? That's what's happening. You see? There's a radial stress going through the radius, and there's a hoop stress. And obviously there's a longitudinal. The longitudinal is there. It's actually the 8 parameter. But in this case, we don't talk about it. I can show you that afterwards. You see it in the textbooks. But the most important analysis is the hoop and the radial. I hope it provides some kind of solace to you, so you can actually see through the wall. Yeah. Okay. So now we have a diameter here. Okay. That guys, how much again? 150. And then on the outside here, I don't want to just is a 450. Okay. So we look at the internal part first, right? What is that internal pressure doing in the walls of the cylinder? In fact, in the whole cylinder, but that's why we don't look at the length. But anyway, you just look at what's happening there, right? So that's what we're going to look at. So we're aware for the internal, like I mentioned to you. When you look at the internal side, we know that it's a maximum on the inner. Am I right on the inner? Is it on the inner? And then it becomes 0 on the outer. Is it? Am I right? Am I right? Keep on forgetting. Yeah. And then this will be 0 MPa at 450.
450.
Okay. Yeah. Now we conduct exactly the same procedure, right? Which you're gonna help me with. So we know radial equals A minus, what is it? B over whatever diameter squared. I'm just gonna call it D to the Dn. So the radial stress at let me do like this rather. 160 times 10 to the power 6 equals A minus B, and we know that's at 0.15 squared. Equation number 1, equation number 2, that's 0 A minus B over 0.45 squared. Once again, students, can you see how important it is to understand the distribution so you know where to put the diameters? I don't know if you guys were battling with that before, but I hope it's clear now. Okay. So your job for me, you find that A and B. All right. Let's find A and B.
A is negative 20 times 10 to the 6.
Are you sure it's negative? I don't agree with you.
No, it's not. It's positive.
Remember,
Maybe it's positive.
positive.
Yeah.
Right though. What is my
It's
B?
negative and it's yeah, it's positive.
What is my B?
4.05 times 10 to the 6.
Yeah.
Okay. My colleagues, the other ones, are you guys keeping up? Who's behind? Ashinda, Lyle, Sibuile, Franco. Okay. Onkuleko. Ronman says good. Okay. All right though. So once you have our parameters, we move on to our hoop stresses, right? So we know that's going to be 20 times 10 to the power 6 plus 4.05 times 10 to the power 6 over some diameter over here, right? We know we're going to input, what's my diameters again? 0.15, and we're going to input a 0.45. You guys can give me that stress. So this will be at my 150, and this will be at my 450. All right. Give me those stresses.
I think it's 200
is
for
200
150.
megapascals.
Okay, yeah. 200 MPa.
And then it's 40
it's 40.
megapascals for 450. Both tensile.
Okay, beautiful. This is what I want. Tensile. That's how engineers speak. Okay. Are we content with this, colleagues? This is for internal. Let's check. Ms. Bono, Mr. Toy, Moses, you guys good?
Good, sir.
100%.
Good,
Thank you, Nathan. Okay. So now we move away from internal and we go external. So now we conduct that analysis. I think there's a short way of doing this, but anyway, let's just stick to the proper stuff, right? So the external side, if you remember, your radial stress, right? The maximum will occur at the outside now, and this is going to be 80 MPa, which is given there, right? At 450. And then you have your radial stress on the inside, that's going to be 0 MPa. What do we do? Exactly the same thing for these parameters now. So your first equation is minus 80 times 10 to the power 6 equals A minus B over 0.45. And we have 0 equals A minus B over 0.15. Consequently, we need a new A and B parameter. Just give me a minute for toilet break quickly.
Did you guys check 1.5? Or? Hello.
One 1.5, this is a new more where you start looking at Poisson's ratio, where it involves strains.
Yeah, 1.5 they ask for strains. But to work out the strain, you need to work out the longitudinal stress. So which diameter must you use for the longitudinal stress?
Remember these Poissons have got ratios, eh? Yeah, they've got different formulas.
Okay, so what is my A and what is my B?
Minus 90 for A.
Okay.
Minus 90 times 10 to the power 6.
Okay, so that's my A, right? So again, you can see on the external side, you're expecting a negative. Because, you know, if you remember the previous one as well. So you can have a negative, so you can have a compressive stress. And what is my B? Minus something. Negative or positive? 2.0. Yeah. 2.5. Okay. Based on that, now you must find our external. Our hoop stress at external, which will be negative that. What is this again? Plus negative 2.025 times 10 to the power 6 over some diameter squared, right? So obviously we know the diameters. You're gonna go in there for me 0.415. We start on the small. Was it 1.5 now? 1.5 and 0.45. Okay, we're getting there now. So that's gonna be. You just tell me what that is. What 150 mole, and this guy's at 450 mole.
150 is minus 18 megapascals compressor.
Okay. Okay, I'm just gonna go 180 MPa compressor. Yes. And the other one?
You have minus 100 megapascals.
Okay.
Same as well.
Compressor. Okay, beautiful. Can you see how we combine 1.2 and 1.3 together? Can you see it, my colleagues? You're getting there now. Moses, Zinke, Machinda, Roderick, Lyle, Charlene, Ferdinand, you good? Bubele?
Yes, sir.
Okay.
Yes, sir. Good.
100%. Now, the question stated, right? They wanted at the mean and all of that other stuff, right? So at the inside and outside, I'm not concerned with the mean. You guys can do the mean, right? Not a problem. But this is what is important. So what we do now, we're gonna draw a table maybe. It's gonna be easier this way. And we're gonna have, I'm gonna go radial here, and I'm gonna go whoop over here. Okay. Well, let me just do it like this, right? So internal, this is for the radial, okay? Then I'm gonna say external. Just draw a line like this. Don't have to do exactly what I'm doing, but it's fine. Our first column will be 150 more. And next one is gonna be 450 more. Okay, just close it off like this. Okay. And then below this is the resultant. Okay, so I'm gonna say that's my internal, external. Okay, yeah, you know what I mean. Okay, resultant. It's quite simple. So we look at the internal, right? At 150 mole, if we go back to the internal, at 150 mole, we had negative 160. We put it over here. We obviously know at 450, it's gonna be 0. Are we happy? Someone saying something. Who's that? Are we happy with that? David is happy. Okay. Then we look at a radial on the external side. In the radial on the external side, it's going to be negative 80 at 450. And we're going to have 0. You guys happy? It's given there. That's the easy part, right? Grand Banks, Ferdinand. Okay. It's quite simple.
Yeah, I'm
Yes.
still here. Yeah, this is a result and it's fine.
Okay, good. So you just add these two together. Obviously, this will be that stage 160 and that stage negative 80. And this is the resultant stress, right? In the actual cylinder. Minus 180, minus 60, and minus 80. But that's only for the radial. So now we can do exactly the same for the hoop. Pull up another table. Internal. Um, 150, 450. Through another line, external. Another line, resultant. Okay. So our internal, over here at 150, we got 200 and the external was 40. So I'm just going to put that in. This is plus, right? 200. What's the other one now? Plus 40, right? We go on the external side. On the external side, we're going to have, is it 100, eh? 100 compressive and 180. So it's 100 negative. And what's the other one? 180 negative. Okay. Colleagues, are you happy? Add them together. We add them together here. And what should we get at 150? What am I getting here? Am I right here? Am I flipping this around?
It's the other way around. Yeah,
Yeah,
that's the other way around.
Yeah, that's what I'm saying. Thank you for picking those. Seeing that one. So over here,
it's negative 180 and then
negative 180, yeah, and negative 100. Yes.
And you get 20 and negative 60.
So you get the positive 20 tensile, and then you get a negative 60. Yeah. Okay. And you can do exactly the same for the mean diameter. So that's a whole other setup there. You know what I mean? Any questions?
So the next question is strain, right?
Yeah.
And you have to work out the longitudinal stress. So do you use the inner or the outer diameter?
I'll tell you now. I'll show you now. Okay. The next question. What is the next question? Okay. But anyway, we're done. We have this for an hour, and I'll show you the longitudinal stress now. Okay, so I'm just asking again, is there any questions? Look at this beautiful stuff, eh? Is there any questions? Moses, Zinke, Maya Pukwa, Sibuire, Lyle, Nathan.
Oh, good, sir.
Okay. All right. So I'm just gonna Paul Franco, thanks. I'm just gonna revert back to the textbook though. And I'm gonna show you something. Okay. I mean, we only have an hour together. It's unfortunate. It's unfortunate for you guys, you know. So the longitudinal stress, right? Like I said to you, its value is actually A. But if you want to compute it by itself, it looks like this. Now I'm trying to look for something here, but I'm not.
Isn't it PD over 40?
No. Remember, this is now for a thick cylinder, man. You know what I mean?
Yeah.
So it's different now. I'm gonna show it to you right now. So I'm gonna show you magic right now.
But I thought that's what the T would be for, the thickness.
Nah. So look. So for a thick cylinder, right? That is the formula. Can you see that?
G squared over T squared minus T squared.
Yeah. So now to verify what I'm saying, right?
Okay, but
yes.
Oh, small diameter. Okay. Yeah.
Yeah. Does it make sense why it must look like this? Because it's a thick cylinder now. You know, it can't be just 4T. I don't know if I'm with you, if you're with me.
Yeah.
Look at if you take where's my internal pressure? This one. So it's 80 megapascals. I'm gonna use it's 450 and 150. Okay. So if I go stress L, is what is the pressure again of the previous problem? 160 MPa. No? This is on the internal side. Times, but the diameter, what was the diameter there again? 0.15 squared. I'm not sure what's the question. Just work this out for me, man. 0.45 squared minus 0.15.
So you also have to work out the longitudinal for internal and external separately, right?
Yes, you understand now why. So work this for me. Work this out.
Yeah.
Just work it out. We'll conclude here. I can see you guys are enjoying your time with me. Too much.
It's 20 megapascals.
20, no?
Yeah, that's what I'm getting. I don't know
But
about
now,
others.
why would the 160 be positive? Why would the 160 be positive this time?
You can make it negative. Doesn't matter to me, right? You happy with that?
They need to be minus, yeah.
Yeah, it's fine, right?
But then wouldn't it? Is it supposed to be negative?
You understand
it was negative.
Now? Yeah, you can make it negative.
Yeah, but
you get my point. You'll get my point now. Yeah. Yes. Must I continue?
Yeah.
Okay. Who's that? Is it Mohammed? No? I don't know who's talking. Who's talking now?
Me.
Okay, cool. Right. So let's go back to the internal side, right? What is my A value here? 20, right?
20.
Yes.
Yeah.
Yeah. So what I'm trying to tell you is that your A. Yeah. Welcome to N6.
All right. Let me just see something. Wait, I'm gonna try something. Hold on. 15 times 10 to the power.
So you can do it for the other one as well. The thing is, your textbooks, let me just check here, doesn't show you the derivation of the stuff, man. If I'm correct. Because if it did, then you would have seen where it comes from, man.
Oh,
like how they derive the formula
okay,
and so
sure.
on.
It works. Yeah, it is
So
the same value.
So just know that A.
So you don't have to work it out.
You don't, exactly. Yeah. That's why I said wait.
All right. Because you need the longitudinal stress in the strain formula, and then the next question is strain.
No, but I was getting there, you know. But yeah, I'm very privileged to have to pick it up again. This is what it looks like in the shell of the thing. I can see the derivations, but it won't be there. You wouldn't need to know that anyway. You see there? Okay, I'm just showing you what it looks like, the element. I want to see if I can find the derivations there somewhere. It's probably some other book, man. Okay. Just having a look here. Okay, my students, so we're basically at the end. What I'm gonna show you now, just what you obviously you have to continue. I mean, yeah. And the next part is to work out strains, right? So obviously if you have a stress, we have a corresponding strain. And yeah, you guys obviously have to just go with the books and whatever. Yeah. So your formulas for the strains.
Excuse me, sir.
Hold on. For the longitudinal, the formula will be like that. For your radial, it'll be like that, which is typically the main one, which is required. And then that's your hoop one. Yes. Go for it.
Okay. So if we do have any questions from the next questions, we can ask you at the next session. Am I right?
Are you asking me if you want to ask me
If
questions?
I can, yeah.
Yes,
Yeah,
so what's supposed to happen? Like you guys send me questions like on a Monday, right?
Okay.
Then I solve them.
Okay.
Is that
Cool.
clear?
Cool.
But the disadvantage of that is that like I'm like I won't be teaching you, I'll just be solving, I'll be assuming that you know. You know what I mean?
Okay.
I don't know if that makes
All right.
sense. Yeah.
No, I
So
understand what you're saying.
yeah. Obviously this is the first session, so I just did it the normal way I normally do it. But I'll be happy if you can, obviously. But what I think I'm gonna do next week, I can tell you right now already, because you guys know that you're writing the other week already, right? I'm telling you right now, it's module 1 and module 2. Focus on the compound stuff. So next week, what I'm going to do, I want to do a compound type question like this, right? If you do, I want to include that to the talk. Make sure you know the talk and the force. It's actually quite easy, but I'm going to do one of those. Then I'm going to do 2 questions or 3, might be 3 questions of the next chapter, tension in the cable. The tension in the cables, just know that there are 2 types of tensions in the cables. One is going to be your normal catenary cable, and one's a parabolic cable, which is typically a suspension bridge, which I highly recommend you focus on. But I will go over that again. I'll try to explain as much as I can, and then yeah. But I want to start with the thick walled compound one, so that you know what I mean. You guys have that.
Okay.
Yeah. Alternatively, you guys send me questions, and I can just solve those ones. I'm supposed to just solve questions anyway. Yeah. But thank you, thank you very much, Roderick.
I need the name of that book.
It's on the group, brother.
Sorry.
Yeah.
Sorry, sir. I want just to.
Yes.
Say the test 1 with module.
It's module 1 and module 2. I sent the planner on the group. Can someone please reshare it again?
And what date is it?
Man, I'm not sure, man. They're supposed to send you the
11.
Yeah, they send the stuff.
11th of February. So it's in 2 weeks' time.
Yeah.
And the other one, test 2?
It's not yet up yet, only test 1.
Yeah. But I gave you approximated dates there on the schedule.
Yeah, I did see the approximated date.
Yeah. But colleagues, all I'm telling you, there's a lot to do. You know? And make sure you're doing push-ups, sit-ups every day. And I mean, you're putting 4 examples.
Gotta hit the gym every day.
Yeah, you gotta put 4 examples in. You know what I mean? You can't be slacking on the stuff. So yeah. Anyway, so next week's objective, unless David sent me a question, I'm doing 1 compound one, which I deem is a good one to do. And I'll do 2 catenary ones. Hopefully 3 if time persists. So anyway, guys, enjoy your evening.
Is it okay next week, Wednesday?
Yes?
Next week, Wednesday again?
Yes, again, 6 o'clock, yeah.
Okay, cool.
Yeah, so again, please don't message me during the day. Keep it in the evening side, particularly before the day before. But we don't worry, we'll figure it out. But what's important here, make sure you put in the work. That's all I can say, colleagues. Put in the work. Yeah. David's already on fire. He's moving already. So if there's any small sticking problems, I can address it as well, right? Because I don't agree with this trimester schedule stuff, but I mean, it's the nature of your beast here. Okay, colleagues, have a good evening. I'll see you next week, man. Cheers.
Okay. See you. Bye.
Cheers.
Bye. Mr. Scholes.
Yes.
You used to teach at CPUT. Yes? You're gone.